Thank you for accepting my talk. Okay. So, this talk is dedicated to memory to those who we lost the COVID-19 pandemic. It was a useless, unnecessary loss. All right, so first I want to thank the organizers and collaborators, NSF. It's about a book that's coming up. Was supposed to be already on the market the day before yesterday, but it's some lag, a few days more. With Daniel Osborne from also from Tallahassee, from FMAU. So it's a summary, just a few select topics. Time would not allow us to talk about everything, right? Just what sort of two types of data that I present, there are more. What is a random object and intrinsic extrinsic data analysis for random objects? Then DNA, the data we consider is DNA, RNA type of data and alphabet-based type of data. And then a little bit more about the phylogenetic spaces, the sticky central limit theorem on spiders, and some space of rooted trees with 3 leaves. And then the question of the origin of space of 4 leaves, which have a very nice geometric presentation. And rooted trees with 4 leaves, right? Unrooted, sorry. And genetic distance and on the origin of the COVID-19 and some more recent work on...
আরে ঠিক আছে আমি ছবি তুলেছি আরে থ্যাংক ইউ কি আছে আমি হোয়াটসঅ্যাপে ছবি ইয়েতে তোমার কি বলে আমি এখানে মানে একটু লেট হয়েছিল জয়েন করতে ডিপার্টমেন্টে এসে জয়েন করলাম ও ভালো করে ছবি টবি তুলে নাও না না এই টক গুলো শুনে না ছবি তোলা অনেক সময় হবে যাই হোক তবু একটা হ্যাঁ বেরিয়ে যাবে বাট স্টিল একটা দুটো লোকের সাথে একটু হাই হ্যালো করে নাও এই তো এই লোকটা যে টক দিচ্ছে স্টিকি সিএলটি নিয়ে বলছে সেকেন্ড কোশ্চেনটা বুঝতে পারলাম না আচ্ছা ডেন্স ওকে তখন ডেভিয়েশন কাপটা কিরকম হবে আচ্ছা একটু ভেবে দেখতে হবে কারণ ডেন্স না হওয়ার কোনো কারণ নেই
I think there is somebody who's turned on their mic, so that's why.
Right. Okay.
But it should be good. No, you can go.
Okay.
Yeah.
Thank you. Some grouping of European languages on spiders, right? So okay. So statistics in changing, and we started to move on from considering just numbers. We've seen in this meeting oftentimes, and. The first person who considered other types of random variables, of course, was Fréchet in 1946. We call them elements, now we call them objects, and they live on object spaces, which is good to have some sort of smooth structure. And examples of such objects are in these books that I'm featuring here. All right, so here is a DNA example related to Cambridge. As you know, DNA was discovered. I hear last night that Watson is the main culprit, but obviously it was experimentally measured by, imaged by Rosalind Franklin. And the images you see here, I guess this is 2 point, right? Are showing a central projection image of the 3D structure from an external point through the crystallography 3D structure. So that's why it looks like center like this, like we are talking about the projective space, but that's related to projective transformations. And all right, so these are polymers made of long chains of nucleotides. We know that for they are coming in base pairs for DNA because it's coming from both parents, and they are aligning, are grouping together, are matching together pairs C and G, cytosine and guanine, and adenine and cytosine, guanine and thiamine, right? So these are their chemical formulas of these compounds. These base pairs are, of course, from both parents. Sometimes, you know, there is a mismatch. People cannot have children, as you know, right? So now, the technique used for alignment is also due to somebody here. It's Zanger. He used clustering. When you align sequences, if you want to build trees, they have to be aligned. So in other words, you have to move them along each other until you get a perfect or almost perfect match. So that was classical Omega software, but not more recently. It's Sudhir Kumar, a biologist, computational biologist, created a way faster tool called molecular evolutionary genetic analysis, the one that we are using here. Now, the problem, like with the last century, where you have, you know, the century of physics, there are good things and bad things that are coming with science. And the good thing, of course, is that you can cure maybe some diseases using new techniques, mRNA techniques, other techniques, but you can also do some harm. We have this Nobel Prize by Jennifer Doudna and Emmanuel Champarty on the CRISPR-Cas methodology, which of course is an older methodology, but they advance it faster. So in other words, you can cut and paste these sequences. And that's another type of data, alphabets. So alphabets are crucial for communications. And the first alphabet is, of course, coming way back from the old ages in thousands of years ago, right? Was the so-called Canaanite alphabet that was like hieroglyphs, was actually pictorial. Each of these signs had a meaning, and they were usually gradually transferred by adding the vowels by the Greeks, and then they were spread through Europe, yielding the languages we speak now. So as you can see, the old letters had a meaning. The Aleph is God, Bet is a house, Gimel is a camel, and Dalet is a door, which are transferred into alphabet Delta and A, B, C, D, as you know. So essentially, these, although we have Indo-European languages, and we have also Sanskrit, Sanskrit has more signs, so this type of alphabet prevailed in building data. So now, what is a random? We'll see how we use this alphabet by the end of this talk. So random objects, of course, random object is just a random variable valued in a metric space. And the metric space, if it has a smooth structure, then you can use one of the distances, the chord distance or the arc or the arc distance. This is the arc distance along the surface, the geodesic. This is the chord distance if you embed the manifold in a higher dimensional space. Of course, chord distances are easier to work with computationally. Therefore, what we call the extrinsic data analysis is faster than intrinsic data analysis. All right, so now the advantage of being smooth is that due to consistency of the Fréchet sample means, essentially your sample means will be close to the population mean. Therefore, you can project on the tangent space at that point and run the analysis almost linearly by some Cramer-Delta method. So that's the way to transfer the central limit theorem from the general numerical case to the manifold case. All right, so now what is a space with a manifold stratification? Probably the best way to think of it is like some manifolds of higher dimension that I glued to lower dimensional subsets in a ordered way, in a filtration way, such that the largest, the dimension of the stratified space is the dimension of the largest so-called stratum. So, and the differences, set differences between strata, consecutive strata, are manifolds. And the most important examples are spaces of trees. Initially, binary trees were considered for central limit theorem by Basrak, but originally the stratified space structure is due to Bilera, Holmes, and Volkmann in a 2001 paper. Other examples are spaces of rooted trees, which are so-called open books. So imagine a book with leaves binding to one lower dimensional subspace, vector subspace. So, okay, so now phylogenetic trees, going to the data analysis, are of course connected directed graphs, and the typical example we have for data, as I mentioned, it's the COVID data. That's the original Wuhan sequences from 2019, just part of it. RNA has the advantage for viruses that has only about 30K letters long, right? So it's easier to align than DNA, which are in the millions, for example, for the human genome. And so there was an interest in the so-called gain of function that was noticed by already in 2018 by Gromov, who was asking himself prior to his retirement, what is going on with these machines that are doing some sort of viruses at an exponential rate. All right, so here's the structure of a simplest possible stratified space. Is the space of 3D leaves, trees with 3 leaves, and they may come in different arrangements. 1, 2, 3. These are essentially the current species that are obtained from their DNA, and they may be in certain orders, these DNA structures. And here in the middle you have the so-called star tree, which is not a binary tree in the sense that you have here 3 leaves sourcing from the same point. So now T4, originally in Bilera and Hoffman, it's a space that looks like this. There are now more possibilities. Essentially, you'll see there, if P is the number of leaves, then there are 2P minus 1 factorial faces for these 3 spaces. And this is the region that was mostly analyzed in recently by, fairly recently, by starting in 2010, right, at University of Chapel Hill. All right, so now this is the general structure. You might have interior edges, and if you have just binary trees, then you have exactly P minus 2 edges. So the dimensionality of the TP space of trees with an unknown root, is P minus 2. And as I mentioned, there are that many orthons. Now, for our analysis, we considered rooted trees. In other words, while in general it was assumed that the ancestor is unknown, we are, for our analysis, we had to assume that we know who is the ancestor. Therefore, we have these rooted trees. Now, here is the geometric realization of the T4. So T4 is a spiky projective excavated dodecahedron, a very nice structure. What does that mean? You are taking a dodecahedron and you push to the center of the dodecahedron, obtaining those 15 faces, but essentially they are 30, but they are coming in pairs, and you identify the opposite points. And since these are those squares that you are seeing in Bilera and Volkmann representation, now you see them in full. And this surface you can embed, because it's a R3 realization, and X and negative S are equivalent, you can embed this in the space of symmetric matrix 3 by 3 symmetric matrix, so in 6 dimensions, which is the lowest dimension so far of embedding. So you can run an extrinsic analysis on these spaces. All right, so now let's go briefly to the central limit theorem on a simpler object space, the so-called spider. You have a number of legs joined at the origin. And now if you have a distribution, you may assume that on this spider, you may assume that it's obtainable by some weighted distribution on the legs and with some probability measure at the center, but usually you don't have data there. So oftentimes we will assume that this will be 0. So therefore the Frechet function, which is the expected, so the distance, by the way, I don't know how to go, probably this is going back. So if I want to find the distance, if 2 points are on the same leg, of course you take the difference between them, but if 2 points are on opposite legs, then you have to take the sum of the distances, obviously. All right, so therefore, the Frechet function can be represented this way. It's sum of integrals, right? Where these are the measures on the legs. And in the end, it turns out that this is a quadratic function. So as simple as that, because the spider is one-dimensional stratified space. And this quadratic function includes this term, which is the integral on leg I of a sort of a mean a weighted mean on that leg. So now you are considering various possibilities. Since the Frechet mean is the minimizer of the Frechet function, of course, this quadratic function is very easy to look at it, right? So what possibilities do we have? We might have this to be, if I'm calling this on each leg, I'm calling this XA, right? This may be positive. Then you will have a unique solution on that leg. And the central limit theorem is a kind of regular central limit theorem. It's a normal distribution. If this is 0, then the limit is folded. I mean, it's a positive truncated normal distribution for that leg. And however, if these differences are all negative, then you do not, the only minimizer is just at the star tree, so-called, at the center of the spider, no matter what. So that is stickiness. In other words, even if you are selecting a sample and you are looking at considering instead of distribution, the empirical distribution, and calculate this, if you get that for the sample, the sample counterparts will be all negatives, no matter what, the sample meat will not budge, will stay there. So that's a stickiness, a simplest case of stickiness. All right, so now going to SARS-CoV data. We had in 2020, I got an email from Science that there is some problem, I don't know, viral disease, don't know what. And I immediately went to check what's going on. And I ran into some data from a southern China university with something called H virus or Wuhan virus. But my Chinese is fairly weak. And, but I had a wonderful student who immediately knew what's going on. I mean, the data, so he selected the data. So there were two types of sequences. Bat viral sequences, and there are the so-called Wuhan viral sequences. And, well, I was wondering what's going on, but I didn't want him to analyze fully this data because, of course, I didn't want to jeopardize him in any way. So I asked somebody else, Roland Moore, he is now in New Mexico working for the Fed. So he was aligning these 72 sequences that we got. And these are the kind of, in mega, right? These are the kind of trees you get. We put at the root either a Wuhan tree or a bat tree. Try to figure it out. What is the shortest, let's say, evolutionary distance to get to the current state from the root state? So the evolutionary distance will tell you which is more likely the ancestor. So this is the entire data aligned, well, a piece of it, because of course there are about 30K such, coordinates, so to speak, right, in each line. And I think in 16 has here an A, which shows that they are not the same, but there are many differences if you're going all the way along. All right, so this is the full, entire sample phylogenetic trees, but can you do statistical analysis with sample size 1? Probably not. So therefore, we divided this data into smaller trees, as I showed you one before, right? Putting at the root either a bat virus or a Wuhan virus. And we consider this genetic distance, the evolutionary distance, being the distance of the trunk length plus the distance of the interior edge length. And that's a spider 3, that's an open book, a product of a spider with 3 legs with an interval 0, 1. And our hypothesis was we accept the bat origin if the mean evolutionary distance for the bat root is more than the mean Wuhan distance, and we accept the other one if the order is the opposite. And so therefore we consider the non-pivotal bootstrap percentile confidence interval for that many samples, because the sample size, imagine if you have 72 divided by, if you want trees with 3 leaves, paired, that's 72 divided by 6, that's exactly 12, right? So sample size is too low to look at asymptotics. And it turns out that the difference between the mean evolutionary distance for the bat and the Wuhan is fairly large. These are the confidence intervals showing that SARS-CoV-2 is most likely a lab-made virus. All right. And, well, now this is recognized already. I've seen news it's recognized in Germany, it's recognized in the States very recently, finally. But the perpetrators are still free. Right. So, okay, so now for the analysis of the European languages, we don't have too much time left. Sorry for that interference. I can talk some other time about this one, right? So the data we are considering is a so-called, it's a standard data set, so-called Maurice Swadesh words data, which can be found on Wikipedia, has 2,000 words in 5 languages, 2,007 words, right? And we are trying to figure out, based on stickiness, if we group these languages in various ways, based on the first letter of certain words, if the data is sticky, that means that there is not much connection between the words in that language, right? If the data is not sticky, there is some relationship. So we calculated this for all sorts of triads, English, French, German, and this is kind of motivating equidistant, that one language is further away from the other two. So the French here is away from English and German, but there are situations when French is a higher distance from these languages. And all right, so given the time constraints, I probably won't go too far. I can continue some other time.
Coffee break.
So anyway, these are the Italian. These are those XA conditions for stickiness. If you remember the XA star, so this shows that there is some sticky situation for these 3 languages. Means that they are fairly close in some sense. All right, so I'm going to just run to the conclusion, right? clustering certain European languages may be done through use of a 3D spider. And here are all sorts of situations. And Swedish list has not been the gold, has been the gold standard in linguistic. Phrases or sequences are of interest as well as for future work. And these are some references. And thank you.
So maybe one quick question before coffee. Yeah, go ahead.
In the last example, instead of looking at letters, I think you should look at sounds. Because, for instance, if you look at freeze
Yeah,
and
that's
feel in
phonemes.
German, then...
Yeah, you mean phonemes.
Phonemes, yeah.
Right, yes. My brother, who's a linguist, right, he told me, why don't you look at that?
Mm-hmm.
I said, well, I was, working with my student for digits. Essentially, it's coming from an example in the book, multivariate book, applied multivariate book by Johnson and Witcher. And so I said, why don't you look at other words? But you are right.
Mm-hmm.
But that works also for other languages, not just those that are grouped by a certain alphabet. It's a different, yes, you are right, but it's a different type of analysis. Yeah.
So maybe let's discuss about coffee with Vic, because it's like coffee. Okay. Thank you very much
Thank
again
you.
for the.